All right. Let's go over the tests quickly. Make sure that you get the right answers, that you read it properly. You're going to see a lot of similar questions on the final. Just change the numbers around and that kind of stuff. So make sure you got it. So the southwest direction is at what azimuth angle? Should be at 225 degrees. Because remember, azimuth, north is 0, 90, 180, 270. So southwest is 225 or 45 degrees from south. We'll start at declination 45 degrees. The circumpolar from Portland, Oregon. Well, Portland, Oregon is at 46. So this is 46 degrees to the north celestial pole. North-south, celestial equator, 90 degrees. Everything circumpolar is within 46 degrees of the north celestial pole either side, while this star is at 45 degrees. So it's right here. So yes, it is 1 degree inside. So yes, it is circumpolar. Which telescope would be best for observing a faint galaxy? Well, faint galaxy, you want as much light as you get. You want the biggest telescope you got. Galaxies are hard to see. So you want the 27-inch. This one, I'm wondering, because when half the class gets the same problem wrong, I wonder if I taught it wrong. So the B minus V for a red star has to be greater than about 1. A lot of people put 0. If B minus V is less than 0, it's usually blue. But in between here, from 0 to 1, it's usually a white star. So a lot of people just say greater than 0. That's not right. It has to be greater than about 1 to be red. Remember, it's a continuum. It's not just all of a sudden it's red. It just kind of gets redder as you go. B minus V can go all the way up to 2 something. The negative side, the blue one, is about the smallest you get, is about a negative 0.5. Telescope with low magnification has a larger field of view. Lower the magnification, bigger part of the sky you see. One reason why the length of a solar day is not constant, there's 2 reasons. One, we're on an elliptical orbit, so sometimes during the orbit we're going faster and sometimes we're going slower. And the other one is because of the tilt of the Earth. Because the ecliptic does not follow the celestial equator, sometimes you're going up, and sometimes it's flat, sometimes it's coming down, depending on what time of year you are. So both those effects. Declination is measured from the celestial equator. Absolute magnitude is measured at 10 parsecs. Star with an hour angle of 3, eastern or western. Remember, positive was western. Eastern is negative. Apparent magnitude of 7.1 visible. No, we can only see down to about a 6 magnitude with your naked eye. Given a star has a rate of ascent of 3 hours, approximately what date will best observe? Remember, it's always best when the sun is opposite in the sky. So what we want is the sun to be at 15 hours or 12 hours away from 3. And remember, if we draw our celestial sphere in an ecliptic, this is 0, 6, 12, 18 for the sun. So the sun is going to be halfway between the autumnal equinox, which is September 21st or 22nd, and December 22nd, which puts it right about now, around November 6th, give or take. Okay. So you need to put it around November. A mirror has a focal ratio of f5. There's still people that get it wrong. Remember, whenever it's a focal ratio with a slash and a number, you just multiply that by the diameter. So in this case, it's just 5 times 560 or 2,800 millimeters. If you change to an eyepiece with a smaller focal length, The smaller focal length, the more magnification, bigger magnification, smaller field of view, so it's going to decrease. Spectral type of stars are the hottest. O stars are the hottest. Is it possible to view Alpha Puppis at declination -56 from Commerce? Remember Commerce, we've done this so many times. This is 33. This is celestial equator, makes this 57. -56 is right here. The star is 1 degree altitude when it's straight south. So it's up for probably like 20 minutes. If you didn't have any trees or anything, you could actually see straight south. Only way you usually get to a horizon is if you're like out on the ocean, then you get a perfect horizon. But other than that, you never usually get that. There's always trees or mountains or something in the way. All right, definitions. Ecliptic, half of the sun on the celestial equator. Sorry, on the celestial sphere. Half the sun on the celestial sphere. Zenith, point directly overhead. Field of view is how much of the sky you can see through a telescope. Declination is how far an object is north or south of the celestial equator. Altitude is how far an object is above the horizon. Azimuth is how far an object is from north measured through the east. Okay, measured counterclockwise, clockwise. Sorry. Right ascension is how far an object is east of the vernal equinox. Limiting magnitude is the faintest magnitude you can see through a telescope with your eye. When you take a picture, you can see much fainter. But with your eye, that's your limiting magnitude. Take a telescope, the fainter you can see. Angular resolution is the smallest angular separation you can see with a given telescope combination. Hour angle, how far an object is east or west of the meridian. Meridian is the imaginary north to south line that goes through the zenith. It also goes through the north celestial pole. Sidereal time is time told by the stars on the right ascension of the meridian. Each of those was worth 2, by the way. Number 1, a star with a declination of -16, while its maximum from Boston be. By the way, I used to live in Boston. Anybody lived in Boston? Anybody visited Boston?
Yeah.
Been to Boston? I lived there for 5 years. That's where I got my PhD. Was at Boston University, right on the Charles.
Oh, wow.
Right across the river from Harvard, we could throw a rock at him. We never did, but we could. All right, North Celestial Pole. So at Boston, your latitude is 42 degrees. North Celestial Pole, celestial equator, 90 degrees away, which makes this 48 degrees. And then you put in the star, which is 16 degrees south of that. So you do 48 minus 16, and you get it has an altitude of 32 degrees, or that is 32 degrees. Newtonian Cassegrain telescopes. The biggest difference is Newtonian sends the light out the side, Cassegrain sends it back through the mirror. So you have a mirror, light comes in, focuses, and a Newtonian, you shoot it out the side. And a Cassegrain, you shoot it back through the center.
Oh, so both of the things are meant?
Yes.
Okay.
They both use the same mirror.
Okay.
It's just what you do with the light after it comes to the focus point. All right, the star rises at 1:06 a.m. And we want to know in 18 days, well, you got to remember it was 4 minutes a day earlier. So 18 times 4 is 72 minutes, or 1 hour and 12 minutes earlier. So now we have to subtract an hour and 12 from an 1:06 a.m. And if you do this properly, you have to borrow. But we borrowed, we don't borrow 10, you borrow 60, because there's 60 minutes. So this actually becomes 1266. I know it's confusing, but it's a base 60 system. And you can't do 6 minus 12, so that becomes a 5. So you got 16 minus, I'm sorry, you can. 6 minus 2 is 4, 6 minus 1 is 5. And then 12 minus 1, that you get 11:54 p.m. Time is stupid. They tried to create a metric time, but it didn't go. Where you have 100 minutes in an hour and 100 seconds in a minute. And then each day would be exactly 10 hours long.
Well, 12 is more divisible than 10.
Well, it just would make adding and subtracting time way easier than it is, but
Yeah.
it'd be weird at first, but once you got used to it,
Metric time.
it's like anything, right? Number 4, you subtract the two magnitudes. You get 8.9, then you take 2.512 raised to that power, and you get 3,632. And star A is brighter, it's the smallest number. Number 5, we have an equation we use to calculate angular resolution. Use this equation, sine of the angle is equal to 1.22 lambda over d. The only thing we have to do is make sure those are in the same units. So I just did it as theta is equal to the inverse sine of 1.22 times 5 times 10 to the minus 7 over 1.5. That way they're both in meters. Or you could have done 500 times 10 to the minus 9th, or 5,000 times 10 to the minus 10th. Either one of those is all the same number. You do this, you get that theta, so you go 2.33 times 10 to the minus 5th degrees. But we usually like it in arc seconds, so when you multiply that by 3,600, you get 0.084 arc seconds. The answer. Number 6, visual limiting magnitude. Use the other equation we have, 2.7 plus 5 log d. And this one, you have to remember that d has to be in millimeters. So I put in as 1.2 meter. Well, that's actually 1,200 millimeters. So you have to do log of 1,200. So that is equal to 18.1. Remember, magnitude has no units. Then the telescope with the focal ratio, well, I have one of these f8s, and I have a diameter of 470. So I just take 8 times 470, which is 3,760 millimeters. Magnification, 3,760 divided by 32, you get 117.5. And the last one is this equation. Again, we just rearrange it. Where I give you the angle and you solve it for the diameter. So this is the angle, this is the equation. We want to solve this for d, so d is actually equal to 1.22 lambda over the sine of theta. I just rearrange the equation. And I have to convert the angle I gave, 1.4 arc seconds, I got to convert that into degrees. So what I know is that there's 3,600 arc seconds in 1 degree, and that's 3.889 times 10 to the minus 4th degrees. I plug all that in. 5 times 10 to the minus 7 over sine of 3.889 times 10 to the minus 4. And you get D is 0.0899 meters, or essentially 9 centimeters. Make sure I total up the numbers. I should have dropped your lowest one. And I put the total wrong on each page in the lower right hand corner. Make sure I total up all the lower right hand corners. Make sure it matches the total off the front. It's out of 125 points. So it's not out of 100. And then I write it as a percentage, but in the D2L or in the grade book, I actually put your number out of 125. It's actually exact. You can make it anything you want. You have any questions about the test? Come see me. If there's anything that you thought was weird, great, or wrong, whatever. If you did poorly, don't panic. We still have the notebook, which is a big chunk. It's like, I don't remember what it is, but it's a big chunk of your grade. Plus, we have a final. We have a couple more homeworks too. So there's still some grades out there. You can still pass the class, or you can still do poorly. Which way you're going to go, right? The notebook is 40% of your grade, so that's a huge chunk of your grade. So make sure your notebook has everything in it. Most of the time when people do poorly on notebook, it's because it's missing stuff. All right, let's talk about new stuff. So far this semester, we learned to set up the telescope. We've looked at Jupiter, we've looked at Saturn. Some of you looked at Venus. Was Venus any good? Venus to me is a waste of time. The only thing cool about Venus is it does show phases. So it looks like a little tiny moon. Right now, actually, it's getting slightly less than half. You're starting to get a crescent Venus, which is kind of cool. But you can't see any detail because Venus is completely covered in clouds. So it's just white. The whole thing is always white. It'll never be anything else. We also looked at colored stars, and we looked at binary stars. We calculated the angular size of several different eyepieces. So, how many of you go outside and are like amateur astronomers and want to look through telescopes and stare at things? And
Come on, no, you did.
want to or have?
Not half.
Oh, want to? Not much opportunity. When I was about 14 years old, I really got into astronomy. And I had a grandfather that was doing it as kind of a hobby, which got me excited. And I built my own telescope, a 6-inch Newtonian telescope. I still have it. It's actually in the back of my truck. But what happens is after you look at the planets and the moon and stuff, you're like, oh, well, what else can you do with your telescope? So now tonight we're going to talk about other things you can look at with your telescope. And these are called, or we amateurs call them, deep space objects. These are other things you try to see in your telescope, which is cool. Fun stuff. Now, one of the things we've already talked about is we've already looked at binary stars. Those are definitely sometimes called deep space objects too, but we're not going to focus on them because we already spent the night looking at them. But it falls into roughly 4 different categories. We have clusters, we have nebula, or nebulas, which is sometimes spelled with an E-S. We have galaxies. And actually, we could do 3 types. It's called 3 types. Each of those has subtypes, so that's why it's confusing. The clusters, there's actually 2 different types of clusters. There's open and globular. Nebula, there's actually several types. There's diffuse. There's planetary. And there's supernova remnants. In galaxies, there's spirals, barred spirals, ellipticals, and irregulars. We're not going to do that many categories because when you go look at things, you'll find that what you're usually looking at are really faint fuzzy patches you can hardly see.
Yeah, well, it's universe, it's the actual pictures.
Yeah, it's not at all like
Yeah.
Hubble Space Telescope pictures. You're like, oh, I think I see it out of the corner of my eye. That's kind of what you're looking for. But amateurs kind of like that because that's the kind of the thrill of the hunt. It's like, oh, am I seeing what I'm looking for? So first thing we're talking about, let's talk about clusters. Let's talk about open clusters. Open clusters are fairly young. They're usually found near the disk of the Milky Way. In fact, almost always, there's a few exceptions, but the disk of the Milky Way, because they're young. If you've taken your Astronomy 1303 class and you talked about star formation, all star formation in the Milky Way comes in the disk where all the gas and dust is. For us, that's that lane going across. So where the Milky Way goes across the sky, that's where you're going to see open clusters. Young, remember this is astronomical terms, young is less than about 1 billion years old. That's considered young. Most of them are on the order of a few 100 million years old.
So less than 1 billion?
Yeah, less than 1 billion.
Okay.
That's 1 gig a year. Giga means billion. Sorry, that's a
You're fine.
shorthand that we use. I use it without thinking, but can you think of an open cluster? Pleiades, good example. Some open clusters you can actually see with just your eyes. Pleiades is one of those you can see with your eye. Did you know the Big Dipper is actually an open cluster? What? It is, but it's so loose in our sky, it's so close to us that we don't see it as a cluster.
Hmm.
But one of those stars, the 7 stars, are all moving exactly together, which is a sign that they're in the same cluster. That's one way you can tell, because the clusters form together in the same cloud, so all the stars are moving together. They have what's called the same proper motion across the sky. All right. The open clusters, there's several others you can see with your naked eye. There's something called the beehive cluster in Cancer, which you can see kind of as a little fuzzy patch out of your eye, corner of your eye. The Hyades, which is the V shape on Taurus, the head, is an actual cluster of stars as well. The Hyades, Hyades, that's also a cluster of stars. Those are famous ones. Good thing about them for a telescope, they're usually fairly bright. They're pretty easy to find. And some of them can be too large for big telescopes. Meaning, if you tried to look at the Pleiades in your 10-inch telescope, you wouldn't see the Pleiades, you would just see a few stars in the middle. It wouldn't look like an open cluster because you can't see the whole thing. The whole thing is fairly big across. It's close to a degree across, and you only see about 1/2 a degree. So the bigger the cluster, the less magnification. Those things like the Pleiades actually look best through our binoculars, way better than they do through a telescope. Same thing with the Andromeda galaxy. It's actually 2 degrees across. It's just so faint you can't see it. Well, in your telescope, you zoom in, you see a little fuzzy patch in the center, and that's it.
Yeah.
All right. So open clusters are very good things to look for. Very fun to look for. Some of them show up really well, and I'm going to give you a list of some of the ones we're going to look for tonight later. All right. The other kind of clusters are globular clusters. These are very old. They're greater than about 10 billion years old. How old is the whole universe?
13.8 billion years.
Yeah, about 13.7, 13.8 billion years old. These can be anywhere from 10 up to 12 some billion years old, meaning these are some of the oldest stars. They formed soon after the universe could form stars. It took a while for it to form stars. These are found in the halo of the galaxy. And around the center. Meaning they aren't around the disk of the galaxy at all, because they were formed actually before the disk was formed. So they're in a random spherical shell around the outside. So we see them best actually looking away from the Milky Way, or if you're looking towards the center of the Milky Way, which constellation towards the center of the Milky Way?
Cygnus.
I'll try again.
Sagittarius.
Sagittarius, thank you. Towards Sagittarius and Scorpio, there's a bunch of globular clusters. But as you get out, like around Cygnus and the other ones further out, you don't see any globular clusters. But you see, if you look away from the Milky Way, you see them. So we see them in all the other constellations in the sky. You see them in like Hercules, Aquarius, Wotes, all those places. There's about 150 of these around the Milky Way.
That we can actually see.
That we can see, yeah, and there might be some we can't see because they get hidden behind all the dust, but that's the ones we know of. Globular clusters, I'm biased towards globular clusters. This is what I did my dissertation research on for 5 years. I studied several 100,000 stars in 19 different globular clusters. So that's what my specialty is actually studying post-main sequence stellar evolution through using globular clusters. Now, I haven't done that in a long time, but that's where what I did when I got my PhD. All right, so those are clusters. Very easy, very fun. I'm going to point out a number of clusters you're going to look at tonight. All right, good ones to find. Let's talk about the nebulas. Oh, they're called globular because when you see them, they kind of look like a glob with a little bit of stars around the edge, depending on it. And so that's, that's astronomers. It's a glob of stars. It's actually several 100,000 stars all in a clump. So these have hundreds of thousands of stars. Some of them can have up to 1 million stars. Omega Centauri has over 1 million stars. Up here, these have hundreds to maybe 1,000 stars. So it has more than 1,000 times less stars than the globular clusters.
I could figure out it was a million, just had something picking it out for them.
How do we do what?
The one galaxy, the one globular that has a million, do they just kind of have a?
How do we know that has 1 million? Yeah, we can determine from the size and the shape and everything what its mass is, and then we go by the mass and we say, oh, well, if that has that much mass, it's either in terms of mass, then it has to have that many stars. So, kind of the same thing we do with the galaxy. Because of our orbital speed, we can figure out what the mass of the galaxy is, and we say, oh, well, if it's that massive, it's made of stars, this is how many stars there are. Man, nobody counts. It's impossible. All right, nebula. These are also really good telescope objects, globular cluster. They're easy to find, easy to distinguish, good things to look at. The size depends on the globular cluster, how close they are to it. Some of them are fairly large. We're going to look at the Hercules, it's one of the bigger ones. But then some are significantly smaller than that too. So none of them are tiny, tiny, but some of them are fainter, not as good as others. All right, nebula. A diffuse nebula, kind of a generic term. Astronomers don't use it, but amateur astronomers do. It's for gas that's just kind of floating out there. And this is where you find new star formation. This diffuse gas is found in giant molecular clouds. If you took 1303, you should talk about giant molecular clouds. That's where stars form. When you form these new stars, they light up part of the cloud. And when they light up that cloud, it starts to glow and we can see it as a diffuse nebula. Okay. So famous ones of these are like the Orion Nebula is probably the most famous. it's actually bright enough that you can see it with your naked eye. Why? Because of the way the galaxy is, we're looking towards the Orion spur. It's not actually an arm of our galaxy. So it has a lot of gas and dust, and we're close to it. And brand new stars are being formed. This lights it up. And we see that glowing gas from where those stars are lighting it up. This is a diffuse type nebula, okay? Technically, we would call it an emission nebula because the gas is glowing actually in color. Usually it glows a reddish color. Okay, you can also get a reflection nebula, which gives you a bluish color. And you get dark nebula too. These are usually faint and kind of difficult to see. The Orion Nebula is kind of an exception. Most of them you have to take good pictures, long pictures to see them. But you can see some of these like around the center of the galaxy, towards Sagittarius. There's the Lagoon Nebula, which is a diffuse one. There's the Trifid Nebula, which is another diffuse nebula. So whenever you have star formation regions, that's where you see these at. Almost all these are found in the Milky Way. Almost all, meaning all of them are found in the Milky Way, because that's where the giant regular clouds are. Okay?
Is that because we can't see really into other?
It means, yeah, if there's no stars forming in them, and the stars only form in that, then they don't light up. So if there's a cloud somewhere else, we wouldn't see it, right? You just look right through it. Planetary nebula. One of the biggest naming errors ever. Has nothing to do with planets. What is a planetary nebula? Yeah, star is dying. What kind of star? High mass or low mass? Low mass star. Star like our sun dies. They eject their outer layers into this cloud of gas, and that cloud of gas then is still excited because the white dwarf left behind is exciting it. It's giving out so much UV radiation, it excites all that gas, and that gas glows as a planetary nebula. So this is old dying stars. At the center of these, you'll find a white dwarf star left over from what's left over. Essentially, it's the exposed core of this dying star. The gas in the outer layer is what's ejected outwards. Famous ones of these are the Ring Nebula, the Dumbbell, the Helix, the Cat's Eye. There's a number of them. Lots of them. What's that? Those are just examples. Tonight you can actually, well, actually you can see all those tonight. Yeah, we'll definitely look at the Ring for sure. The Dumbbell is pretty good too. The Dumbbell is supposed to be like a dumbbell weight. Looks more like an apple that somebody's eating, you know, the apple core. Yeah. They're kind of fuzzy. So because it's just glowing gas, so there's no distinct edges, but you can definitely see the glowing gas. The thing about planetaries, they're fairly bright. They're brighter than diffuse nebulas, but some of them are very small. Some of them are almost the size of a star. So you're like, is that a nebula or a star? Okay. But some of the bigger ones are very nice to look at. Supernova remnants. Again, dying stars, but these stars die spectacularly, right? They explode. The most famous is the Crab Nebula in Taurus, also known as M1, which is not up tonight for us. Maybe by the end of the semester, we might be able to pick it up. It's in the constellation of Taurus. But we can see the Veil Nebula, which is up in Cygnus. We can see that tonight. It's a much older one. The Crab Nebula went off in 1054. Yeah, see, we remembered something from our astronomy classes. 1054, we know exactly when that went off. The Veil Nebula was actually like 10,000 years ago. Okay, we don't know the exact date, but it's been quite a while. So it's expanded further. It's kind of this ring. You just kind of see these clouds, these outer clouds that are still kind of lit up. You kind of see it as a wispy cloud that looks like in their wispy glowing thing. These are usually faint. They're much rarer, so you don't see as many of these, but there's a few around. Okay. All right, then we're going to talk about galaxies. I'll talk about them over here. The problem with galaxies is they are very faint. And so when you try to look at galaxies, they make fabulous pictures, but they're not really good to look at through a telescope because all you see is a little bit of fuzz.
Also exposure pictures.
Yeah, if you take a long exposure, all of a sudden you're like, whoa, that's cool. But when you try to look at it, you're going, well, I think there's something there. So they're kind of rough, but we'll look for a few of those too. We have ones all different sizes. Like I said, the Andromeda galaxy is actually 2 degrees across, but you can't see that with your naked eye. It's too faint. But if you take pictures and people take pictures all night, all of a sudden, it's 4 times the size of the full moon. But you don't see that. All you see is this little central bulge. It has companion galaxies too, next to it. Okay. But there's some very famous ones. M51, I don't know if you've heard of the Whirlpool.
Is this spirals or is it just general galaxies?
General, these are spirals. Andromeda is a spiral galaxy, but there are general ones. M81 and M82 are cool because there's 2 different galaxies. And they're right next to each other. Or one is edge on, one's this way. And they ran into each other.
Yeah.
So that's kind of cool. We will look at galaxies. The problem is they're very faint. They're hard to see. And so the best thing to do is to use the lowest magnification you can. You're like, oh, if it's faint, you should use higher magnification. That actually makes it worse. Because if you have like a galaxy, a faint galaxy that looks like this, if you blow it up really big, like this, the problem is it only is that much light. You spread that light over a bigger area, so it actually makes it fainter. It's better to have all the light concentrated in one area. So you want it as low in magnification as you can to just try to even see it. So it's one of those counterintuitive things. But low magnification is better for fainter objects for your eye. If you use a photograph, you don't have to worry about that. You just take a longer picture. So galaxies are tough to see. We will try to see them a couple tonight. Definitely, you can always see the Andromeda galaxy. You can see the Andromeda galaxy with your naked eye. In fact, I'll point it out to you tonight so you can see where it is. It's just fun to say because then you can say, hey, that is the most distant thing you can see with your naked eye. And when you look at it, you go, hey, that light that's hitting my eye left there 2.2 million years ago. 2.2 million years ago, there were no humans. We were still apes in the trees of Africa. A lot has changed since then, right?
Mm-hmm.
All right. So, a couple more things I want to talk about. When they started looking at all this stuff with telescopes way back in the day, there was a guy who became famous. His name was Charles Messier, a Frenchman. And what he did is he was actually looking for comets. Most comets are still found by amateurs. They just go out at night, they look at the sky, and they try to look for something that wasn't supposed to be there, and all of a sudden, if they see a fuzzy patch and then it moves, they're like, hey, I discovered a comet. Most comets, well, up until recently, most comets were still discovered by amateurs. Nowadays, they do have these telescopes that take pictures of the sky every night long, and they find lots of those kind of things, but yes. But Charles Messier said, okay, if I'm looking for comets, and I see all this other stuff, most of this looks like faint little fuzzy patches, just like a comet does. But the difference is none of these move. They always have the same right ascension declination. So he would make a chart of it, mark it down, and say, oh, then he just started numbering it. And so he had his numbers, I think, go to like 1 to like 103, I think it is. Somewhere around 100. And so there are 100 different objects in the sky. The good thing was is he did it back in the 1700s. With the telescope, that's not nearly as good as the telescope you're using today. And he saw all these objects. So these objects became real famous for amateur astronomers because it's like they're really easy to find. And they become fun things to look at. So I'm going to give you a bunch of stuff to put in your notebook. So if you're interested in going outside and looking for things, you have a small telescope or even a pair of binoculars. This will have a list of double stars that are good to see. It also has the list that Messier had of different objects. And then Messier, he didn't get all the objects that are out there. So they started a new catalog, a guy named Herschel, who was, what was her famous Herschel famous for, anybody remember?
Discovering Neptune?
Uranus. And we actually think it was his sister Caroline that did it, but he got credit for it, but they were working together, so we give them both credit nowadays. But he also started a catalog because he kept finding other things that Charles Messier had missed. He created a catalog. It was called the Galactic Catalog, and then they started adding to it. It became a new Galactic Catalog, and now we just call them NGC for the number. So the NGC catalog now has thousands of objects in it. And on your hand pad, look, here's your hand pad. You have different things. One of them is NGC. So if you know the NGC number of an object, you just put the object in, it'll go to that. There's also one that just has M, number 3. M stands for Messier object, all right? So if you go look at an object like the hot globular cluster Hercules, you just type M13. So you just have to know the number, okay? Now, what I've also done is I made a list of good things to look at this time of year. So, ignore the double stars on top because we're not going to do those. We already did those. I want you as a group to look for 3 different nebulas tonight, 2 galaxies, and 3 different clusters. And on the clusters, you have to have both globular and open cluster. You can have 2 of whichever one you want. Essentially 3 of each, but galaxies you only have to do 2, okay? And the 2 can't include Andromeda. That's cheating. It's too easy. Andromeda's M31, so you can't choose M31. And so you're going to go look for those objects. Also tonight is I want you to compare how it looks through different telescopes. So there's a couple of objects we want to look at different telescopes. I'm going to open up our 27-inch, which is the really big telescope, so you can look through that. And we're going to look through that. We're going to look through at something like probably one of the globular clusters. You're going to look at it in your 10-inch. And you're going to look at it through the 27-inch and see how it looks different, okay? I also want one group tonight. We also have an 8-inch. So 2 of you will do the 10 inches, 1 of you are going to do the 8-inch, okay? Works exactly the same as the 10-inch, setup and everything. It's just a little bit smaller, which is good in some ways. Remember I was telling you want less magnification? If it's a big object you're looking at, it actually looks better in an 8-inch than it does in a 10-inch. So those are things that we're going to try out tonight, okay? So if you don't decide amongst yourselves, Dr. Davis will just assign somebody to do the 8-inch. So you get the first sheet, just take it, but if nobody takes it, the last group there's going to end up doing the 8-inch telescope, okay?
So are we just one big, one that's actually getting set up, and then one that's small?
So you're going to set up your own telescope like normal.
Okay.
Okay. And then one of the groups is going to set up an 8-inch.
Okay.
But there'll be a point in the night where I say, okay, everybody go to the same object. We'll all go look at the same object, and you're going to just go around to the different telescopes and see it. We're also going to pull out our $2,000 pair of binoculars so you look through too, which is very nice. So All right, I'll see you out at the observatory.
Dr. Montgomery.
Yeah.
Where did you?
Oh, hold it.
Oh,
You're also gonna be doing a lot of these tonight, so I printed out a whole bunch more, so grab 3 or 4 of these, right? Because every object has to have its own spot tonight, so.
do you know where you want these yet?
No, you'll put it in your notebook.
Yeah.
Under tonight, so you want it chronological, under observations.
So like in between these.
Or behind it or something.
Okay. Make sure because- But, okay.
You already have
Well, we're
one.
gonna print them out later.
With the those supernova galaxies, will we be able to see the neutron stars?
We're gonna send all the pictures
No.
No.
Yeah, you can start
I mean, I
to.
still have it all.
They're just one galaxy only
Yeah,
about 14 miles across.
exactly. We think they give off a lot of light, but there's none of them that you can actually see in visible light.
Quark stars.
Well, I should say that, we can see the, one in the crack, which is a pulsar, we can see that. in the-
I mean, we're
So
fine.
yes, you can. I shouldn't say that, but it's rare. Most of them pulsate radio and you don't see them.
I imagine quark stars, if they exist, wouldn't be much different because they exist right on that knife's edge of total operating limit between a black hole and a neutron star. So
Yeah, it's the same thing. We only see them if they pulsate.